Hey, we North, Mr. Yergler here again to talk about electron shielding with the use of tons of pictures. I want to get started with a definition. This definition I took from boundless.com. It's kind of like a Wikipedia page. It's a little more credible. Anytime you pull something from one of those sites, you always want to make sure, check in a few different places to make sure it's a good, accurate definition. I know what shielding is, and so I kind of knew right off the bat that this was a good definition, but if I didn't, I would want to check in a few different places or check references or something like that on the Wikipedia page to make sure that it's a reliable source. Okay, so electrons in an atom can shield each other from the pole of the nucleus. This effect is called the shielding effect. And describes the decrease in attraction between an electron and the nucleus in any atom with more than one electron shell. The more electron shells there are, the greater the shielding effect. Okay, now that is kind of a lot of jargon that might not make a lot of sense. So let's look at a picture and a simplified definition. Electrons in energy levels closer to the nucleus effectively shield the outside electrons, or the valence electrons, from the positive pole of the nucleus. So what this means is that if you look at an electron in the third shell, like right here, this electron is being shielded from the positive attraction forces from the nucleus. So remember that the nucleus is positive, the electrons are negative, right? So they're going to attract each other. However, there's other electrons in between the nucleus and that outside electron, and so those electrons, those inside electrons, shield that attraction force. Okay, I like to use an analogy to kind of help understand how this works or why it happens. A good analogy is music concerts. This guy right here is Andrea Bocelli. He's a opera singer. I went to a concert and sat in the very front row at the concert. So there was literally no shielding. I got the full effect of the music, the full effect of the speakers, the stage, and all of that. He's got a great voice. Google him if you've never heard of him. Okay, now if we want to go to a different concert, maybe Taylor Swift, for example. I've never been to a T Swift concert, but wouldn't mind going, I suppose. And whoever took this picture is kind of partially shielded, right? There's quite a few people in between the person and the stage, and so the music, the effect of the music, the speakers, the volume, all of those things are somewhat shielded by these other people that are in between the stage and the observer, or the person taking the picture. If we look at another example, this is a bunch of people waiting for a Mumford & Sons concert. If we look at this guy right here, he is very, very shielded from the stage. There's a lot of people in between him, right? And it looks like it's a flat ground, so he probably can't really see the stage at all, which kind of explains why he's bored and looking at his cell phone. So if he was an electron and the stage is the nucleus, then the effect of the stage, or the effect of the nucleus's pull, is being kind of absorbed or kind of shielded by all these people in between him and the nucleus, or him and the stage, right? So this analogy kind of helps to understand why this happens, but it's a little off because it doesn't exactly describe how it happens. In the analogy, in the music concert analogy, these people are kind of absorbing or blocking the sound from the stage, but in an atom, it kind of acts a little bit differently, or kind of happens a little bit differently. So let's go back to the atom. Here's a zoomed in picture of an atom. Here we have the nucleus, which would be positive, and the negative electrons. Now, in the stage analogy, or in the music analogy, this attraction force is kind of absorbed or blocked by the other people in the concert, or in the auditorium. That's not really happening in an atom. This electron is still getting the full effect of the nucleus. It's the full attraction force. However, there are other forces at play. When you have electrons in between that outside electron and the nucleus, remember that all the electrons are negative, so they're going to repel each other constantly. So every electron is repelling every other electron. And so the total force, you could say, is decreased because you have these repulsion forces pushing back on the electron, and then you have the attraction force that is always there, always felt. And we can look at another example of this using the cloud model of the atom, which is a little bit different. So same thing is happening. We're just not showing the individual electrons because we're showing them as an electron cloud, which is a little more accurate. And the main thing that this picture is showing is that if we're looking at this particular electron or an electron in this location, only the electrons in between that electron and the nucleus are going to have an effect, right? If there's more electrons way out here, they're not going to have any negative effect on the attraction force between these two parts of the atom. Only the electrons in between these can be pushing away. Remember that there's those repulsion forces pushing away from the nucleus, and those are the important ones that cause the shielding. Okay, so now you kind of understand how shielding works and what it is, and that's great. But who cares, right? Why is this important? If we want to look at two similar atoms, sodium and potassium, and there's also a picture of lithium here. These are all in group 1, I believe, or group 2, one of those two. I can't remember off the top of my head. And so they're very similar in reactivity, but potassium is more reactive than sodium. And the reason that this is the case is because of shielding. So if you look at these two electrons right here, which one is more shielded? There's a lot more electrons in between this electron and its nucleus than there are between this electron and its nucleus, right? There's a whole nother ring of electrons. And so this electron is a lot more shielded than this electron is. And that makes it a lot easier to remove because there's more repulsion forces from these other electrons pushing away on that electron. And so this electron would be easier to be removed from that atom and go and bond with something else. And when electrons leave and when they come and attach to other atoms, whenever electrons are moving, you typically have chemical reactions, right? And potassium is a lot more reactive than sodium because that outside electron is so much easier to remove than sodium's outside electron. Part of that is also the distance. Notice the size of the atom. We know from Coulombic attractions that the distance makes a big difference in how well that electron is attracted to and held together to that nucleus. So the further out it is, the easier it is to remove, and the more shielded it is, the easier it is to remove. Okay, so that is shielding. If you have questions, be sure to ask your teacher or send an email, and make sure you get any confusion cleared up before we move on. Okay, this is Mr. Yergler signing out.